Today we got to talk about binary search trees. So, and I do have a mic now, right? Yeah. Okay. Just be whispered. Yeah. I went over my solutions. The solutions to those actually are pretty short. I could probably say them pretty succinctly. With functional programming, the code is so expressive, like I kept saying. My solutions for those, you know what? I'm not even gonna. My TAs get mad at me whenever I say any property of my solution. They're like, every student takes that as pure gold. That like that's what it has to be. So I won't even go in there. But it's very compact code for the solutions to these if you're really leveraging functional programming. Anyway, binary search trees. Let's talk about what these are. We're going to talk about this as an application of trees. We have this idea of a data structure, a node-based data structure that has references to two child nodes, and we saw some of the implications of this, some of the applications of this structure in expression trees. Now let's talk about binary search trees, which is something that is a fundamental data structure in computer science. This is something that whether you know you're using it or not, you're going to use this throughout your entire career. These are very useful, very helpful data structures. And usually you'll use some data structure that happens to be based on a binary search tree. So you won't always know that you're using them directly. But they are very prevalent. These are used quite often. The lecture question today is take a binary search tree and return a list containing all the values in the binary search tree in sorted order. So traversing this tree using the traversals that we talked about last time, traverse this tree, gather all those values into a list, and then return that list is what we want to do today. So a binary search tree is a tree which happens to be the tree that I used for an example last time happened to be in the format of a binary search tree, and I talked about that a little bit last time, but let's go into more depth and more formally define this. So a binary search tree is going to be a tree where all of the values for any node in the tree, for every single node in the tree, all of the values in its left subtree are less than that node's value. So if I take any node and look at all of the values in the left subtree, they'll all be less than. All values in the right subtree are greater than, and this applies to each node. This node, the same is true. This node, the same is true. And any duplicate values are going to depend on our specific implementation. So if I had 2 5s in this tree, where that second 5 goes is going to be dependent on the application. So the equality, that can vary based on implementation, but the less than and greater than, or specifically using some arbitrary comparator, if that comparator is true or false, that's where the values are going to end up going. But if the comparator is false in both directions, if A compare B and B compare A are both false, that behavior is not defined specifically by BSTs, by the root definition of a BST. It's up to the implementation. Sometimes, and the reason why this is important, is sometimes duplicates are just flat out not allowed. So if you want to implement a set data structure, thinking of like 191, that mathematical definition of a set, where duplicates are not allowed, in code, we typically build that using a BST, and then when we insert a value that's already in the set or in the tree, we just don't allow that duplicate. So sometimes we don't want to allow ties at all, and that's an important feature. How we decide to handle those tie values is going to change the behavior and change the functionality of our BST. For my implementation, I'm just going to throw ties to the left. The implementation that's in the code, in the examples repo, I throw ties to the left. As long as you're consistent, it doesn't matter which way you choose, unless you're not allowing duplicates. So let's take a look at a BST in our code. And this is, on the top level, this is what a BST is going to be for our purposes. We want to take a generic type, just like we have before, take in a comparator just like our sorting methods have before, where that's going to determine how we're going to enforce the property of a BST. When on the previous slide I said less than and greater than, but the comparator can be any arbitrary comparator that we're given when the BST is created. That comparator is going to be the same throughout the lifetime of this tree, so all elements in this tree are going to be subject to the same comparator. And we're going to have two methods. And we're going to only store the root node. So similar to the linked list. When I adjusted my chair. Yeah, I am a McNair scholar. We could talk about that. But I highly recommend the program. Dr. Ott, she's awesome. They'll get you set up. Like, if you're interested in grad school, especially PhD, go check them out. So we're only going to store the root of the tree. This is similar to the trees that we saw on Friday. And Heather, I was trying to think of her name. Dr. Ott and Heather. We're only going to store the root node of the tree, or just like we had linked lists, we would store the head of the linked list. So here, same thing applies. A binary search tree is only going to have a reference to the root node, but we're going to kind of have this wrapper class to be able to add some BST-specific functionality, namely the comparator and any methods that we implement. We don't want our nodes themselves to implement these methods because there are some things that we have to be concerned about the entire structure of the tree. So we're going to store the root inside this BST, just like we did the stack in Q. We did the same thing. We stored the head, and in the Q case, the head and tail inside that kind of wrapper structure. Next, we're going to see two methods. We're just going to build two methods for this BST, insert and find. So insert a value of type A into this tree. We don't need to return anything. We could return a reference to the node that was created, sometimes a feature. We're not going to return anything. We're just going to insert it into the BST while respecting the comparator, while having that comparator apply to the structure after the insertion. It's going to be the key important part of insert. And then find, given some value A, find a value such that A compare that value and that value compare A are both false, meaning that they are equivalent compared according to this comparator. Find a value and return the node in that case. This time we are going to return the node. Return the node that stores the value that we found that is equivalent to A compared to this, according to this comparator. So our usage here, we have this class, and I should mention we haven't defined insert and find yet. These are I have the syntax here wouldn't compile. We have a concrete class but abstract methods. I'm just doing that because we're going to fill out these methods later. I just want to show right now that these are the methods that we're going to have eventually. We'll define them inside this class. For the rest of the lecture, we'll see the implementations of both of those methods. So to create one of those, we need one of these BSTs. We're going to need to define our comparator. I'm just going to use the less than with ints. Keep it simple as we're talking. Dang, my mouse. Every time I tap that mouse wheel, I have to disable the wheel, I think. But I'll have my comparator just be less than with ints. Create a new BST of type int. Give it that comparator. And now I'm going to have a BST structure that's going to store these ints in a sorted, not necessarily sorted order, but an order compared to that's going to keep the structure of the BST according to this comparator. And then I'm going to insert a bunch of values into it and hope that I get the structure that I expect. Of course, we're going to. And then we can call find on this BST as well. So if you can see from the usage, if I didn't call this binary search tree and I didn't call my variable BST, you wouldn't know that this is a tree at all. You wouldn't know it's a binary search tree at all. You're just inserting elements into a structure. You can find elements in it, and we're going to see that we can access these elements in sorted order. If this were named something else, you would never know it's a tree, and that's the case in certain data structures out there in the wild. You'll be using a binary search tree, you just won't know it. For example, I believe C++'s map is a maps and sets. I believe those are both based on binary search trees. But you wouldn't know it by their names. Just a map, you think of a key value pair, a key value store, but it's actually based on a binary search tree. So let's look at these two methods and see how they would be implemented. So the find method, given a value that we want to find, let's find it in this binary search tree. If we do find it, we're going to return that node. We want a reference to the node that stores that value that's equivalent to the one we're looking for. If it's not found at all, we're going to return node. And to implement this functionality, we're going to, these are kind of our base cases here. To implement this functionality, if the value we're looking for is less than the node, the value at the node that we're currently looking at, we're going to move to the left and make a recursive call on the left child. If what we're looking for is greater than the value that we're looking at the current node, we're going to move to the right child. So you can see that we're directly leveraging the structure of a BST, using that comparator and saying if that comparator says that the value we're looking for is less than the value we're looking at, then by the definition of a BST, the value I'm looking for, if it's in this tree at all, has to be in the left subtree, because that's where all the values are that are less than the value I'm looking at. The whole right tree has values that are greater than what I'm looking at, so I don't need to look at the right subtree at all. I'm only going to look at the left subtree. And same thing, if the value is greater than, we don't have to look at the left subtree at all, because everything in the left subtree is less than the value of the node we're looking at. So we're directly leveraging that structure, that BST structure, to know where to look to find the value we're looking for. So with this in the code, we're going to have actually two methods that we implement here. I've mentioned this briefly, but today we're going to get two examples of seeing this directly, and I recommend it for the lecture question as well, that we're going to have two versions, so to say, of this method, or rather a helper method, as my naming implies. We're going to have find A. This is the interface method. When somebody wants to know where a node, wants to get a node, this is what they want to call. Find me the node, the value I'm looking for. Give me a node, give me the node where it lives. This is all a user cares about when they're calling the find method. Here's a value I want to find. If you have a data structure and you want to find a value, this is what you want to look at. Find me this value, tell me where it is. That's how a user wants to react to this. But with this method header, with this input and this output, it's a little tough to write the method to be able to get that done. We would like a second parameter to know what node we're currently visiting, and then navigate through this tree visiting various nodes, while always knowing which node we're currently visiting. Now, of course, you could try to write this in a non-recursive way and not have two methods. But as I mentioned last lecture, it gets very tough to do with trees. I recommend anyone who's not a believer in recursion yet, try to write this iteratively and just see how that looks. You can do it. You can definitely get the job done, but it's going to be a lot more painful. Actually, I take that back. With find, it's not all that bad. But with the traversals, try to write your lecture question without recursion. That's a bit tougher. Yes, you can use var. So the restrictions are off. You can use var, you can use control flow. Everything's fine. There's no more restrictions for the rest of the course, unless you're doing the old assignments. So I'm going to call this find helper. I'm just going to defer to this. Find helper is going to look for this element, A, and also have the node that we're currently looking at. A reference to the node that we're currently visiting, and then we're going to navigate through this tree by calling this method with different nodes that we're visiting throughout the run of this algorithm. And then find itself is just going to defer to the find helper and say, look, you're going to start at the root. You're currently visiting the root. You're looking for A. Do your thing. But we wouldn't want to expose this to the user. We wouldn't want a user to have to say, find A and start at the root. A user shouldn't have to define that because that should be implied. So we have these two different methods to be able to imply that starting at the root behavior. If the value, so the find helper, this is what's going to do the real work. This is what's really implementing the algorithm. And we have two base cases here. If the node we're looking at is null, so we navigated our way to a leaf of this, well, not necessarily a leaf, but if we navigated our way to a null node, then we haven't found what we're looking for. We're just going to return null, and that's going to be the definition of our user-facing interface. The user knows if they call find of A and A is not in this tree, that they should expect null to be returned, just the way that we have this set up. You could handle this in different ways. I'm just going to return null and call it a day with that. Otherwise, our two recursive steps are going to be if A is less than, or rather, according to this comparator, if A should come before node.value in the fully sorted order, then I'm going to move to the left subtree, make the recursive call. I'm still looking for A, but I'm going to move to the left subtree and make that recursive call over there. So that node.left is now the node that we're currently visiting, looking for this value A. Else, so if A does not come before the value, let's check if the value comes before A. If that's the case, that's the same as saying the value that the value that we're looking for, comes after this node's value in the fully sorted order. We're going to make that recursive call on the right subtree. We're going to move to that right node and still looking for the value A. Still looking for A, but move to the right subtree. We know we can eliminate the entire left subtree. If this is true, we know we can eliminate the entire right subtree, and we can start narrowing down our search quite quickly, as it turns out, using this method. If A doesn't come before value, and value doesn't come before A, and the node we're looking at is not null, that means we found what we're looking for. We found what we're looking for, so we can just return a reference to that node, because this is where we are. If both of these are false, then node.value and A are effectively equivalent. The comparator was defined in the constructor. So the constructor takes the comparator, and then we pass a comparator in when we define a new binary search tree. And then this find method and find helper, this is defined inside the binary search tree class, not the binary tree node class, if there was confusion there. This is inside the binary search tree class that takes a comparator, has a reference to the root, and then find, this is what we're implementing right now, but we're still inside the binary search tree class, just to give a roadmap of where we are in this. So we're implementing find right now. Well, we've implemented find. We'll see an example of it now. We've implemented find, and then we're going to implement insert after we go through that. Both these methods that we're looking for are defined inside the binary search tree class. And of course, the full code is in the repo if you want to check that out and see how it all fits together in one class as well. The value of the tree would be in string, right? So does comparator convert to double int and compare them? For this example that we're looking at, the type parameter is int. So we're comparing ints directly. We're not messing around with strings right now. You may be thinking of the expression tree from the last lecture question where we had strings and had to convert to doubles. But this time the binary search tree type parameter is directly int. So we're only working with ints here. All right, so let's see an example of this. So say this is the binary search tree we have. This is the one I created on the other slide. And we want to find the value 4 in this tree. We're going to start at the root, compare that value. We're going to do a simple comparison. To pull out our comparator and say, is the value I'm looking for, does this value come before the value I'm at the node that I'm currently visiting in the sorted order? That's going to be true, so we're going to move to the left subtree. We're going to do the same comparison. We're going to say, is the value I'm looking for 4? Does it come before 2? No, it doesn't come before 2, so I'm going to eliminate the entire left subtree. Then we're going to check, does the value I'm looking at this node come before the value I'm looking for? That's going to be true. or 4 comes after 2 in our sorted order. So we're going to move to the right subtree, and now we're going to check, does the value I'm looking for come before this value in the sorted order? That's false. So does the value I'm looking at come before the value I'm looking for in the full sorted order? That's also false. Since those are both false, we must have an equality according to this comparator, and then we can return this node. So this node gets returned back up the recursion, gets returned back up the recursion, gets returned back up the recursion, and then that call to find is going to return this, a reference to this node right here. That's the node that's going to be returned. I feel weird. That's one of those parts where I would always stop and ask for questions, but since you can ask questions all along, I'm just going to keep going, I suppose. I'll try to break myself of the habit of stopping for questions. Maybe I should still stop just so we have time to digest what happens, but hey, you can rewatch the videos too, I suppose. So let's look at insert. So we saw how to find, how we're leveraging the structure of a BST to always find a value efficiently. And actually, I do want to talk about this a little bit more. This is I feel the same way. Recursion makes my heart feel so full too. Recursion is just such a cool thing. Once you get used to it, it takes a while to wrap your head around. Once you wrap your head around it, man, it's so cool. It's a very powerful thing. So this what we just did here is effectively, at least asymptotic in terms of asymptotic runtime, this is effectively binary search that we just did. When we have a tree like this, specifically a balanced tree, meaning that that we have this nice structure that we like, which we'll talk about towards the end of the slides here. When we have this structure, each time we make one comparison, we're comparing 5 and the value we're looking for. Each time we make that comparison, we're eliminating half of the search space. And we're moving down just with one comparison. We eliminated all of this search space and narrowed it down to just this. One more comparison, we eliminated half the search space again, then actually found what we're looking for. So, since we're halving the search space every time, if we have a search space of size n, and each comparison we're halving the search space, it's going to take log n comparisons to be able to get to the value, either the value we're looking for, or to realize that the value we're looking for doesn't exist in this tree. It's going to be a log n algorithm, so very efficient, very quick find implementation here. Effectively binary search. If we had an array of sorted values and ran binary search on it, we're effectively making the same comparisons with the same efficiency. So when we and if you do a Google search for recursion, it always, you know what, let's take we take one little breather here, right? Maybe that's something I should do, just kind of step away from, Google's silly. Just kind of step away from the presentation a little bit. Did you mean recursion? Did you mean recursion? Yes, I meant recursion. So let's figure out how to insert into a binary search tree. So with find, we were leveraging the structure of a binary search tree. With insert, we have to be careful to preserve that structure. So we're going to assume that when insert is called, that our binary search tree has the structure that we intend. And when we insert, after that insertion is made, we have to make sure that it still has that structure. If we're not inserting in the right spot, if we insert, say we have a value that's smaller than the root, but we end up moving to the right subtree and insert it somewhere over there, well, we just broke everything to do with binary search trees because we no longer have the one property that binary search trees are supposed to have, and that the left subtree has all the values that are less than, the right subtree has all values that are greater than, and that should be true for all nodes. Once we break that, we don't have a binary search tree anymore. So how do we insert while keeping that property? We're going to set up a helper method just like we did before, except now our base insert has a little bit of work to do. If the root is null, so if I have a completely empty tree and I'm inserting into that empty tree, well, I just inserted the root. That's going to be the new root. So I have to update that reference to root to be a new node with no children, just a single value in this tree with that value A, and there's nothing else to do. If this is not an empty tree, then I got to go to my recursion and start at the root with my recursive algorithm. Which is going to have the node that we're currently visiting and the value that we want to insert into this tree, just like we had before. Except insert, we don't have to return anything. We're not returning a node. We're just modifying this tree. And notably, these are not immutable trees. These are definitely mutable trees. We're changing the crap out of these things every time we insert. But we're going to change this tree. We're going to have the side effect of having this value in this binary tree after this call is done. Is there a name for if order isn't preserved? It would just be a tree at that point. It would no longer have the property of being a binary search tree, but it would still be a tree. It just wouldn't have that structure. So just a plain old tree at that point. So insert, we're going to check. Effectively, what we're going to do on a high level, the high level description is we're going to run find until we find a null value, and that's where our node goes. And for my implementation, again, we talked about this earlier. If there's a duplicate, I'm breaking all ties arbitrarily going to the left subtree. So we just have to pick a strategy. I decided to allow duplicates and move all ties to the left. So I'm going to compare the value that I'm looking at, the current node that I'm considering, with the value I'm looking for, or the value that I'm inserting. If the value I'm looking at comes before the value I'm inserting, we know we have to go to the right subtree to insert this value. So this means that the value I'm looking for, or the value that I'm inserting, comes after strictly after the value that I'm currently considering, the node that I'm currently visiting. We move into the right subtree. If this node's right child is null, there is no right subtree. So I found where I can insert. I found room in this tree to be able to insert this node. Node.right, instead of being null, you're now going to be a new node with the value that I'm inserting, and it's going to be a leaf. We have no children off of this new node. It's just this value A. A node containing this value A and not having any children, no subtrees. If the right child is not null, now we have to hit our recursion. Okay, that wasn't null, but I know that's the direction we need to go in. So let's make the recursive call of this helper method. We're still inserting the same value, but we're going to recursively call this on the node's right child, move to the right subtree, and see where we can insert this thing over there, and start the call over again. If this value we're inserting doesn't come strictly after the value we're considering, then we're going to hit our else, and we know we want to move to the left subtree, and this is how we're breaking those ties arbitrarily. We're going to move duplicates to the left subtree. That's we're taking care of that through our else. So this is a strictly less than. Is this value less than A? No, then A must be, then the value must be greater than or equal to, which means we're going to go to the left subtree, and all ties are going to end up in the left subtree. If that left child is null, we found a spot, we found room in this tree where we can insert this value that we're inserting, and instead of being null, the left subchild is now going to be this new node containing the value that we just inserted. Insert that, and then return back up the recursion. Else, put a new recursive call on the stack. Technically not, because this is tail recursive, but make a new recursive call of this value that we're inserting on that left child. Start looking in that left subtree, because somewhere in that left subtree there's going to be a spot for this new value we're adding. So move over there and start the process over again, start the recursion over again. And we're going to keep doing that until we find our base case of some null value that preserves the structure of this tree. Once we find that first null that preserves the structure, that's where we're going to insert. So if we want to insert a value into this tree, let's say right before we added 7, how did we add 7? We're going to compare 7 to the root. That root, 7 comes strictly after that. According to our code, we would compare 5 comparator 7. That's going to return and say, hey, 5 comes before 7 in your total sorted order. So we're going to move to the right subtree. The right subtree, we're going to check, does 8 come strictly before 7 in this sorted order? That's going to return false. 8 does not come before 7, so either 7 is tied with 8 or it comes before. We're going to look to the left subtree. We're going to find that the left subtree is null. So we found a spot where this value fits that preserves our structure. Now, every time we visited a node, we used our comparator to enforce the structure. So when we had 5, we were checking the structure. Okay, which subtree, according to our definition of a BST, should this value go in? The right subtree. 8, which subtree should this value go in? The left subtree. Then that left subtree happened to be null. So we found a spot where 7 can go. It fits into this tree. All of the structure is preserved. And we have a functioning insert method that, given a BST, preserves that BST property and maintains that property. So we can still have a BST after that value is inserted. Well, if we wanted to add 9 to the tree, excellent example. I'm glad you asked. So if we want to add 9 to the tree, 9 would come after 5, so we'd go to the right subtree. It would come after 8, so we'd go to the right subtree, and come before 14. So 9 would end up being the left child of this node 14, and it would end up going right here, according to our algorithm. So, and we would just repeat that process no matter what we're doing. If after that we want to add, let's say 10, we would go right subtree, left subtree, and then I'm running out of room here, but and then right subtree again. So we'd have 14, left subtree is 9, or left child is 9, and then the right child of 9 would be 10 after that. We would just keep going, following that same strategy until we find a null, and then we would add it there. What if the number repeats? So what if, say we wanted to add 4? According to my algorithm, I broke ties by arbitrarily putting them to the left. So if we want to add 4, we would go to the left subtree, right subtree, and then here we would have a tie. My algorithm breaks ties by going to the left subtree, so we'd add 4 right here. And I do that right here. So I only compare once. If we think of this as less than, if the value of this node is less than A, go to the right, else go to the left. So that else is taking care of the ties. If node.value and A are the same, so if this is 4 less than 4, false, go over here and insert into the left subtree. Or we could make, this is where if you had a set or anything where you don't want duplicates, you would make another comparison. You would say else if comparator of A node.value, then go to the left, else don't do anything, don't allow the duplicate. That's where you would modify this code if you don't want to allow duplicates. No, we're not creating a new tree. So this is a mutable tree. We are actually changing the tree. So anybody with a reference to the same BST or any subtree or any node in this BST, we are actually messing everybody up. So we're not enforcing immutability here. We're not making a whole new tree. We're just the root of that tree that we started with now has an extra node. If you traverse that root again after, there's actually an extra node in there, an extra value that's going to be visited. So we definitely change things. We do not have immutability. We don't have the features of immutability here. So let's revisit our traversal. I mentioned this last lecture, but let's talk about it now. this if we do an in order, I mentioned it very briefly. It might have even been during the Q&A, to be honest. Everything blends together now. But an in order traversal, if we do an in order traversal over a BST, we actually get all of our values in sorted order, just based on that one property that defines a BST. If we visit any node, say we're visiting the root node, what an in-order traversal does is visits all of the left subtree, then this node, then all of the right subtree. Well, our BST says everything in the left subtree is less than this value, or equal to in our case. Everything in the left subtree is less than or equal to. Everything in the right subtree is greater than. So if we print all these values, then print this value, then print all these values, we're going to maintain that sorted order. In just my example, I was pointing to the root, but since this property is true for every node, we're going to print the left subtree, all the values that are less than, then this value, then the right subtree, all the values that are greater than. Just by combining the way an in-order traversal traverses and the property of a BST, we have to be printing these out in sorted order when we do an in-order traversal over a BST. So we actually have this sorted order. This is how a BST maintains a sorted order based on a comparator, because we can do an in-order traversal and find all the values, visit all the values in sorted order. So if we want to iterate over this and iterate over values in this sorted order for whatever reason, we're going to pull out our in-order traversal code, and that's how we're going to iterate through these values. We're going to go left, left, visit, visit, right, visit, done, visit, right, visit, 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 and then we get all of those values in the correct order. If correct is sorted. Visit, what is that word? It means we're... How do I define visit? It means we go to that node. In this case, visit, I'm using visit to mean print to the screen, because we're printing the values. So we would print this value, print this value, print this value, return, print this value, recursive call, print this value, print this value, return, and then return. So visit in this case means print. It's apply whatever function we were given to each one of the nodes. You are welcome. If there was a 3 in the left of 4, what would it do? Would it do the 4 first, or all the left parts of the 4? Okay, if there was a 3 to the left of 4, then we would still get left, print, make the right call, make the left call, print 3. That would return. We'd print this, make the call on null, which would just return, and then return back up, and then print 5. So we'd still get that in the right order. Just based on the in-order traversal, we're going to visit the left, we're going to go to make the recursive call on the left, apply the function to that node, then make the recursive call on the right. So when we make this recursive call, we've already printed 2, -3 and 2. We'd make the recursive call on the left, print the 3. That would return, then print the 4, make the recursive call on the right, return, then print 5. So we would still get -3, 2, 3, 4, 5. Just based on the order that we make the recursive calls. Why does in-order traversal require a function parameter? It doesn't. That's just the way that we did our in-order traversals. That's the way I defined them in this class. You could have it just default to printing or default to doing whatever functionality you want, but I wanted to bring back first-order functions and make sure you don't forget about those. Those still do exist. We still have a comparator function that we took for BSTs. We can still give our traversals functions to apply, but you could do these in. You could write an in-order traversal, like for example, your modified in-order traversal for Friday's lecture question probably didn't take a really shouldn't take a function parameter because it has a very specific purpose. But if we want a general case in order traversal, which is effectively the for each function, we actually built our in order, actually all three of our traversals that we saw on Friday were effectively for each methods that apply to trees that call for each in different orders based on which traversal we chose. So it's basically an implementation of for each. We could change that function parameter and change that to like map or reduce or other methods. But that's just the way that I set it up, just to show you what these traversals are from a theoretical side. I need to understand what these traversals are, so like you could sketch them out on paper, go through a tree and talk about what a traversal is. That's something you'll probably be asked to do at some point in your careers, during interviews usually. All right, let's talk about efficiency for a little bit. Again, I'll repeat this throughout the whole semester, but we're not too concerned about efficiency in this class. But I do want to talk about it whenever we're talking about something that is really related to efficiency, which we're definitely talking about right now. So these trees, I mentioned this balanced, and I foreshadowed this slide a little bit. A balanced tree means that for every single node in the tree, the number of nodes in its left and right subtrees are equal. If we have that, then we have a fully balanced tree. And as long as we're close to that, we have different definitions of balanced to say that, well, it's close enough to being perfectly balanced. For example, if I added one element to this tree, it actually can't be balanced after that, because once I remove the root, the subtrees have to have unequal numbers. One of them's going to have 4 elements, and one's going to have 3. So we can't always be perfectly balanced, but as long as we're close enough to this to our definition of perfectly balanced, we'll refer to it as balanced based on some formal definitions that we can define. For example, if the right and left subtrees, the heights are different by only 1 is typical definition. Anyway, if a BST is balanced, then we have some really nice properties in terms of efficiency of these algorithms. If it's balanced, each time we visit a left or right subchild, as we saw with our search method, we're eliminating half of the nodes in the tree that are remaining. So if we're always visiting the either left or right child and navigating through the tree, we're going to reach a leaf of a tree, which is a node with no children. We're going to reach a leaf of the tree in O of log n time. Since we're cutting this search space in half each time we visit a subtree, that subtree has half as many nodes as the node we were just visiting, as the subtree that's rooted by the node we were just visiting. So if we do that log n times, we're going to go from n to 1 and have a subtree of size 1. So since the height of the tree is log n, find is going to take log n, and insert is going to take log n, because both of those methods rely on navigating through the tree until we find a null. We might find it before we even reach a leaf, but worst case, it's going to take log n steps, order of log n steps. So find takes log of n, and if we can insert in log of n, insert and find in log of n, if this is a balanced tree, we actually have another sorting method, and this I mentioned briefly in an earlier lecture as well. If we can insert in log n, then we insert n elements into a brand new BST and then do an in-order traversal on that tree, and we've effectively sorted in n log n time. So this is another way that we can sort, is by throwing all of our values in a tree and then navigating that tree in order traversal, get all the values in sorted order. We just sorted in n log n time. So it's another sorting algorithm that we have, that we can have at our disposal, that we could have. We don't really know how to do that yet. But it's another method we could have if we can insert in log n time. So there's one big advantage of this that we haven't seen in our other sorting algorithms. Any sorting you've seen so far, at least in 115 and 116, The O is big O notation for asymptotic notation. The sorting algorithms that we've seen in 115 and 116 all assume that you already have the n elements in typically in an array, and then we sort all those elements in n log n time. But we didn't really have an efficient way to insert new elements into that sorted list. In fact, if it's in an array, we can use binary search to figure out where to insert in log n time. But when we insert, that's actually going to take O of n time to do an insert. If, say, we insert a value at the front of the array, we have to copy all of the rest of the array, all n values, down one index. That's going to take O of n time. A linked list, we can insert really efficiently if we have a reference to where we need to find, but we can't do binary search on a linked list because we'd have to navigate. It takes O of n time just to find. It takes n over 2 calls to next, n over 2 hops just to find the midpoint of a linked list. So binary search is ineffective. Binary search doesn't work on a linked list. You could simulate it, but it's not going to be n log n. It's not going to be log n. It's going to be whatever you end up doing is going to be at best linear runtime. You could iterate through the whole linked list, copy all those values into an array, and then run binary search, but it's already log n at that, or it's already O of n at that point. So you don't have an efficient way to insert into an array or a linked list, maintain sorted order, and be efficient. You just can't do that. So if you want to maintain sorted order while elements are being added and even removed, if you have a dynamic structure which is changing a lot, but you always want it to be in sorted order at any given time, you want to be able to navigate over those elements in sorted order, a binary search tree is what you're looking at. Binary search tree does have more features, more power than our arrays and linked lists when it comes to sorting. Or else it's just give me all n elements. Once I'm absolutely sure I have all n elements, then I can sort. If that's not the case, BST is going to come to your rescue. Is that the widely accepted definition of a balanced tree? This is a widely accepted definition of a perfectly balanced tree. And then balanced tree depends on your application. As long as, I'd say for asymptotics, I'm trying to remember the exact definitions we use. As long as the difference between the right and subtrees sizes differ by a constant, then we're going to consider that balanced in terms of asymptotics, because we don't care about constants anyway. Does a BST always have its smaller value on the left and larger values on the right? Kinda. It depends on the comparator. Like if the comparator was the greater than, then it's backwards from that. But the values on the left are all values for which that value take the comparator and compare that value with the root node. It's always going to return false, and then it's always true for the right side. And then with the falses, if reversing the order also returns false, those ties have to be broken in some way. Some scheme has to be decided. But according to your comparator, the values that come before that node according to the comparator would go on the left, and right on the other side. I've never seen a tree backwards. I suppose you could build one that's backwards, but it's common convention that left comes before, right comes after. Or else your in-order traversal will give you the reversed order. Unless your in-order traversal goes to the right first and then the left, but that's just silly at that point. What about space complexity? It's O of n. We don't have any wasted space here. Tree versus linked list. It's the same, asymptotically anyway, the same space complexity. So there's one huge problem here, though. All of this depends on having a balanced tree. Well, what if our tree isn't balanced? Using our insert method that we saw, if I insert values in sorted order, I'm actually going to end up with a tree looking like this. This is effectively a linked list at this point. I'm going to have O of n insert, O of n find, using the implementation of a BST that I just showed you. So we actually don't get balanced trees using what we've seen today in lecture, using what's in the repo. We don't get that inefficiency that we want from this specific implementation of a BST. This is a problem. Not a problem that we're going to solve in 116, but this is a problem that needs to be addressed if we're going to use these trees for their efficiency. If we're going to use them for efficiency and then inserting sorted values just blows everything up, I mean, that's just not good. That's not something we can tolerate. So we need some way to insert in log of n time. We still want efficient inserts, but also maintain the balanced structure of the tree. So we want a balanced BST with log n insert. We could do this with like O of n insert just by looking at all the structure of the tree, rebuilding the entire thing every time. That wouldn't be too hard to implement. But how do we do that in log n time? Maintain the sorted order, maintain the balanced structure, maintain the everything with the tree, but in log n time. And duplicates, I mentioned that throughout the lecture, but we have to decide on duplicates. And the answers to these questions and more, way more, come in CSE 250. So in CSE 250, you're going to study what are called self-balancing binary search trees, and they are going to achieve this. In log n time, they're going to be able to insert and restructure only small portions of the tree up to log n nodes will be updated, and you'll see how the tree can actually modify small parts of its structure as elements are inserted to fix the sorted order. So if we have something like this, by the time we insert this 4, these self-balancing algorithms, I think at the 4, I don't recall exactly off the top of my head, but when this 4 is inserted, for example, assuming we didn't insert any of these yet, what you can do is have a self-balancing tree rotate these nodes so that 2 becomes the root, -3 becomes 2's left child, and 4 is 2's right subchild. And with that restructure, we can maintain that balanced property of a BST. Then we can add 5, and when we add 7, do some more rotations and be able to get that structure. So that's something you'll look at in CSE 250 is how to actually achieve this, and going through all those details of trees that restructure themselves to maintain balance.